Okay, I think it's slowed down a bit. I want to welcome you to the November meeting of the Marin chapter of California Native Plant Society. I'm Dave Long, the co-president of the chapter, and it's our pleasure this evening to have meteorologist Darren Peck with us, who is a meteorologist at KPIX-TV, the CBS affiliate in the San Francisco Bay Area. During his talk, I would appreciate if you would mute yourself. There'll be a chance to ask questions at the end, and I always encourage you to put questions into the chat while you remember them. And a little background about Darren. He's previously been a meteorologist in a number of other cities and weather forecaster at TV stations in Seattle, in Sacramento, in Las Vegas, Orange County, and starting out in Flagstaff, Arizona. He's received 2 Emmy Awards for on-air performance and is a certified broadcast meteorologist by the American Meteorologist Society, which is a mark of professional distinction and recognition. He grew up in Southern California, and then in his late teens, he spent 2 summers in Yosemite National Park and fell in love with Northern California and developed a passion to better understand the natural world. And after that, he returned home to California State University, Northridge, and got a degree in physical geography with a focus on climatology and geomorphology. So it's my pleasure to turn the meeting over to Darren to talk about a subject that we would all like to know more about, the weather.
Well, thank you very much, Dave, for that introduction. And also thanks to Ann Elliott it was her idea to have me do this talk, because Ann saw me give a talk very similar to the one I'm going to share with you guys tonight for the Friends of Mount Tam. And the Friends of Mount Tam had invited me up, this was about a month ago, for their Science Quest Day, which is where they have talks and hikes throughout the day on the mountain. And they'd asked me to come and talk about the weather on Mount Tam. So the talk I'm going to give to you guys tonight is largely that talk, which was focused on mainly the marine layer and what it makes it such a unique aspect of the weather, not only on Mount Tam, but also across Marin County and Northern California as a whole. But I'm going to add on to that talk a little bit tonight because I've got a little more time. And because we're coming towards the time of the year where the marine layer is not going to be as big an influence in our lives weather-wise. And there are other things to discuss, such as what happens here in the fall and what this winter might look like in terms of any long-term predictions. And I'm also going to use part of a long, about a 14-minute long edition that I did for CBS News Bay Area, discussing La Nina and how that might impact us this winter, but also giving a little bit of background into what La Nina is exactly, how it differs from El Nino. A lot of that stuff is general knowledge. I have a good feeling most people tuning into this tonight are already pretty well versed on that. So I'll skip over some of the basics and I'll talk to you about what we should or should not expect from this particular winter, which is a La Nina, but it's a particular categorized type of La Nina. And I'll discuss why we shouldn't maybe put too much weight into that for this winter. And I'll give you some examples for why I would say that. All right, that's the intro. And I'll just go straight into the discussion from here, Dave. So I guess I could share my screen. Would this be a good time to do that? Yeah? Let's see. So I'll also say before I do that.
Please share. That's
okay, here we go. And I'll also say that as I do that, I'm at a bit of a disadvantage because I've been a TV meteorologist for 25 years. And the talk that Ann saw me give was in person, where I was in front of the images you're going to see. And I have 25 years of habit and reliance on interacting with these graphics in person. You could probably, humorously image what a weather anchor does when they're gesticulating in front of maps and pointing to things and spinning around. And it's like I'm doing calisthenics up there sometimes. So I won't be able to do that tonight in this presentation. And hopefully you'll bear with me on that. And the images will have to speak for themselves along with the narration. So we're going to start with, and probably the first half of this talk is going to be focused on the uniqueness of the marine layer. And I'm going to share the screen now and show you what is a gorgeous time lapse that I captured from our camera that sits on top of the Salesforce Tower. This was back over the course of the summer. And before I hit play on this, and we're going to watch the marine layer animate on, we're probably all well oriented with what we're looking at there. I think the silhouette of Mount Tam is unmistakable. So that's the vantage point. You can also see Sausalito in the foreground. And you'll see the lights come on for Sausalito as well as we play this forward. And I'm just going to animate this. And of course, you're seeing the marine layer now sped up. And as cool as it is to watch this, there's a couple of features I want you to look at specifically. If you look at the hills where Sausalito is, the fog's doing something really spectacular. It doesn't really have a technical name, but I think if you just refer to it simply as a fog fall, you'll see what I'm trying to talk about there. Now the lights are coming on, by the way. So you can see the hills, the homes. You can even see 101 there in the background, zipping along up there along the shores there through Richardson Bay. And as the sun goes down, we kind of lose our vantage point on that. I can just bring it back again. So I think the marine layer is probably one of the most dominating and inspiring aspects of the weather here in the Bay and in Marin in general. And I'm going to show you one other time lapse of this to maybe share a little bit of the beauty of this. And instead of being on top of the Salesforce Tower, this vantage point comes from the top of Mount Diablo, which makes this a really unique way to look at this. So kind of like the two notable peaks, really, through this part of the bay, like the two main locators. You're looking at Mount Tam, and you can see Mount Tam right here, off in the distance, from Mount Diablo. And for reference, there's Highway 24, snaking its way down from the Caldecott Tunnel, which sits up right about here. These are the East Bay Hills. You're seeing the same fog fall happening here. This is where Sausalito would be right in about here. And as I play it, you'll see there's a fog fall happening there. You'll also see in the foreground, there's one happening here. And then there's another one out here, which is probably Bolinas Ridge, stretching off to the north. And what I also want you to watch for as I play this is, there are two different distinct directions you're going to see the clouds moving. The Pacific Ocean sits out here in the background. There's the horizon. Watch the motion the clouds are moving back there in contrast to what's happening in the foreground, and I'll hit play. So there's a lot to see here. Marine layers surging onshore in the foreground, doing those really cool fog falls over the East Bay Hills. But at the same time, you can clearly see there's a different direction. There's a strong northerly flow over the ocean out here. And this is a 90-degree angle. And here comes sunset. Really cool. I'll just pause it there. You get these beautiful colors. And you can see clearly now as the light goes, there's a wave happening here in the marine layer. It takes a little bit of a dip here, rises up, and then kind of does a smaller little dip beyond it, which really helps us visualize that this is a fluid, obviously, just like water in a stream. And just as water in a stream, when it moves over a rock or a boulder, you'll see it go through those dips and rebounds, those wavy patterns. Well, the marine layer is doing the same exact thing, only you don't get to see it until you time lapse it. But that fog fall in the foreground there, and also out here in what we saw, is an interesting item to talk about what's controlling this. So the first thing to discuss in terms of, if we're going to talk about the marine layer, and by the way, there's your satellite image, the big picture view. I'm going to go back to that time lapse for 1 second before we come to this, just to set the stage for what we mean when we say marine layer. Sometimes people will just call this broad blanket fog. Oh, the fog's coming in. Other people will choose to label this the marine layer. Oh, the marine layer's coming in. And the truth is, the majority of what we experience here is not technically either of those. First of all, for something to be labeled fog, the technical definition of fog is a cloud that is on the ground. The base of that cloud has to be touching the ground in order for a technical definition of fog. Now, some of this is doing that. And when you're on the Golden Gate Bridge and you're driving through this, you are in fog. And it is accurate to label it fog at that point. But the majority of times, you're actually not. And the fog is above the deck of the bridge, or the base of it is certainly above your head. In which case, to be technical about it, you're really just talking about a stratus cloud. So that cloud itself, in some case, you can see here as it's going, if you're standing on the East Bay Hills, you're in fog. If you're standing out over here, or out in the foreground here where these clouds are passing over your head, you're no longer in fog. You got to call it a stratus cloud. And you can't really call that cloud the marine layer either. And I'll get to that in 1 second, because I want to tell you exactly what we mean, what the technical definition of marine layer is, because it's not the cloud deck. All right, let's move on to the next image, and hopefully these will all become clear as I go along. That's a beautiful satellite image to show you how this looks on the big picture view. Clearly, that stratus cloud within the marine layer, and sometimes it's fog, is following a very distinct pattern here, one of which I'm sure you're all very familiar with. It's over the ocean and just barely over the coastline. But if you look at the Golden Gate, right through here, a very distinct little signature is happening. So when we were looking at that time lapse and you were seeing the clouds which were moving directly down from the north, we looked at that direction when we were seeing the clouds over the ocean. And I said, look at the deck of clouds over here coming in through the Golden Gate. It's moving at a 90-degree angle. It's moving differently. Well, there's your onshore surge of what we would say, for simplification at this point, the marine layer, which is surging inland through the Golden Gate, which just happens to be the only opening along the California coastline and really along the west coast of North America for about 1,000 miles. This is the only gap where this deck of stratus cloud, which forms out here in summer so regularly over these cold ocean waters, this is the only place where you get a little gap like that where it can stream through. And if you take a look at what's happening here, those clouds that we were watching in that time lapse as they were streaming in, on that day happened to be going over the East Bay Hills. On this day, they're stopping because they're not high enough to get over them. And that little region over there in the East Bay Hills, where we've got all of those smaller, lesser known redwood parks, they've all been logged and they're second growth redwoods now. But historically, there has been claims made from the scientific communities who study the historic range of redwoods that before they were logged, the largest redwoods in California were there in the East Bay Hills. And when you look at this satellite imagery, and when you take in the picture of a whole, there's a fire hose of stratus cloud or fog when it hits those hills, regularly streaming in all summer long through the Golden Gate, pointed directly at those East Bay Hills. And it's the fog drip that redwoods really love, among many other things, when it comes to drainage basins and flatlands and the like. But that little signature right there, when it comes to how does the marine layer interact with the plant life that we all love so much, that is so distinctive about California, this is one little side trip I'm taking with you, which I think is just a fantastic awareness of the marine layer's role, how it behaves, and its impact, at least on that one little localized spot. You've probably all heard the stories, or maybe many of you have heard the stories of how before those trees were logged, there were 2 huge redwoods on that ridge on the East Bay Hills that were used as a navigation point when people came in and sailed in through the Golden Gate in the late 1800s. Just to give you an idea on the trees. But I digress, and I'll try not to get too far off track. I just thought that was a fascinating aspect of this. We're going out now to a slightly wider view to help us grasp the idea of not only the marine layer, but what's driving it, which is the Pacific Ocean directly off the coast of California. So when you take a look at a wider view, that stratus cloud within the marine layer is a pretty wide area. which just happens to correspond to another image shared from NASA. And what we're seeing here now is NASA using satellites to detect certain traces of biological readings on the sea surface temperatures. It's color coded. And when you start to get into those bright shades of green that you're seeing along the coast, that's where the satellites are detecting what we know are phytoplankton blooms. There's a great deal of nutrient and ocean life found off the coast of California. And if you look at where that plume is, where you've got that really concentrated area of bright green, high concentrations of phytoplankton, and if we just back up for a second, it corresponds with where you also see that deck of clouds, which seems to be a permanent fixture off the coast of California for 5 months or more, 6 months or more, out of the year here, what we think of as the marine layer. There is a connection between these two, and that's the connection I want to try and make in terms of the marine layer significance, its uniqueness, and the effects it has here in California. And the next image will help drive that point home for me. When we get into the summer here, California has a unique climate, as you all know, our Mediterranean climate, where it doesn't rain in the summer. At the same time, we've got the marine layer. The two go hand in hand. We get a persistent marine layer off the coast. We don't get rain. And the driving factor behind that is a semi-permanent ridge of high pressure that sets up over this section of the Pacific Ocean each summer. And a couple of things that happen with that. A big center of high pressure, obviously, this is the reason we don't get rain. It's a blocking high. The storms can't get through it. So that in a simplified way, covers the no rain in summer. But what's the connection between no rain and our constant deck of clouds, stratus cloud, fog, marine layer? And that has to do with the way that high is spinning. And I'm sure you all know, high pressure spin clockwise. Take a look off the coast of California. All summer long, due to the intensity and the persistence of this center of high pressure sitting right here, there is a constant flow of wind along the Pacific Ocean out here that is coming from the north. And as that northerly wind, with enough regular momentum, moves across the surface of the ocean, it starts washing away the surface waters. They get pushed away. And as a result, something's got to come up to replace it. And that's what we'll see happen here in the next image. So this schematic, picture, there's the California coastline. Picture that's like Mount Tam or Big Sur. The arrow is moving from the north to the south. So the schematic we're looking at is a little askew, but in general, our familiarity with the California coastline makes that pretty intuitive to see what we're looking at here. We're looking at the coastline, and you can see that arrow showing you a northerly wind moving away the surface waters along our coast, which then have to be replaced. It's just a matter of physics. If you're going to move that water out of the way, something's going to rush in to replace it. And that's where the upwelling happens. And that's what creates the California current, which I'm sure is another term many, if not all of you, are very well familiar with. But just a little bit of a background to how that California current forms. The water that's replacing it is getting pulled up from depths that are down at about 400 feet deep off our coast. It is much colder down there. And that's why it is so darn cold off the coast of California. If you look at coastlines at our latitude on the other side of the country, on average, they are notably warmer than we are. We spend most of the summer with our sea surface temperatures in the mid-50s. For comparison, you could be upper 60s, I would assume 70 or so along the eastern border. But I'm going to show you sea surface temperatures in the 80s here across a crucial part of the globe coming up in a second. But ours are typically in the mid-50s. It's not fun to get in the water here in the summer. But that upwelling is crucial for two things. One, that's where all the nutrients are, so you're constantly pulling up nutrients from depth. That's why we get the phytoplankton blooms. I'm not an oceanographer or, a sea life expert by any means, but apparently there's a lot more nutrients at 400 feet down. And if you keep pulling that water up to the surface to replace the water that's constantly getting pulled away by our consistent north wind off the coast in the summer, thanks to that blocking high, you're now putting a lot more nutrients in the coast. And it's why we've got such a show happening off of our coast. This is why we can't go crabbing right now, because there are so many humpback whales here that are taking advantage of this, because of the whole chain of life that feeds off that. So that's where we get that's the definition of the California current right there and what drives it. Here's the impact that has here at home. If we take a look at the globe, these are sea surface temperatures. Remember, I was saying ours are in the mid-50s. Where you look down into those deep shades of red near the equator, that's more like low 80s. So these are average sea surface temperatures. We're going to look at anomalies later in this talk. But this is an image which is helpful to start with to understand how unique the California current is. If you look off the coast of California over here, you can see the cold water. You can kind of make out what's going on over here on the eastern seaboard. Over there, you've got the Gulf Stream. There's a whole other list of things at play, but there's clearly a huge difference at our latitude. It's very rarely that cool, and it's because of that constant northerly wind and the upwelling that takes place. So there's a view of the California current in one way. But since we've now got this steady pool of relatively cold sea surface temperatures sitting out there in the mid-50s all summer, that has an impact on the layer of air sitting directly above it, and that's where we come to this term, marine layer. So if you've got this steady supply, let's bring that back. If you've got this steady supply of refrigerant sitting out there, and that's kind of the descriptor I like to use for this, that cold body of water there is having an effect on the surface of the air directly above it. And it is that layer of air, which is outlined here, that we refer to as the marine layer. It's totally different than what the air mass is over the rest of California. This is why it can be 105 in Sacramento in the summer, while you need a jacket at the coast at Stinson Beach down here, and you're barely at 60 degrees. That's because you are within that marine layer. This is the definition of marine layer. It's not the cloud. That's a stratus cloud or fog. Those are the two ways to really, if you want to be technical, to refer to that. When we say marine layer in the meteorological community, the literal definition of that is this layer of air, which is changeable throughout the course of summer. And the level of it will change. And the height of that marine layer makes all the difference in terms of the weather that we experience throughout the Bay Area. Sometimes this level right here can be as much as 2,500 feet high, in which case this marine layer is now getting high enough, it's getting pulled in above all the mountains, and it's going all the way to Concord, and they cool down. If we're under a center of high pressure in the summer here over land, which is pushing down, that's the very nature of high pressure, you are exerting pressure downward on the surface of the Earth, and that's where this marine layer will get compressed, squashed. A compressed marine layer, instead of being 2,500 feet high, it'll only be maybe 1,200 feet high. As it was earlier this summer, I'm going to play this animation forward to this point, and then I'm going to fill in some numbers here in a second. But there was a really unique occurrence on Mount Tam earlier this summer when we were going through a heat wave. And this is real early. I think this was back in May. And it was really an opportunity to drive home the point of how significant the influence of the marine layer can be. At 10 o'clock on this particular morning, when this marine layer was at about 1,500 feet high, there was a very unique spread in temperatures. On Mount Tam, on this particular morning, I think this was back in May when I did this and when we experienced this, it was 94 degrees on the summit of Mount Tam at 2,500 feet, and down on Panoramic Highway near the Homewood Inn, 1,000 feet lower, it was 55 degrees. at the same exact time. That's really weird. It's very unique. And it's probably the most exaggerated aha moment of the intense influence living within a marine layer can have. Oftentimes we think about losing the benefit or the influence of the marine layer by going inland. Oh, the Tri-Valley has to suffer through so much heat in the summer, while those of us in Marin are usually much cooler. And we simplify this often by thinking that's just because if you go inland, you get away from the coast. And that's true, but that's not the only way. Oftentimes, you can leave the influence of the marine layer simply by rising above it. And once you can step in a situation like this, if the marine layer is only 1,500 feet, Mount Tam is going to be a whole lot warmer like it was here. So this was the original inspiration for this talk for the Friends of Mount Tam to discuss the influence of the marine layer locally here. And I think this is, at least for half the year, one of the most important features of the weather here in Marin and in the Bay Area as a whole. And let's see where we're going to go with this next. I'm going to bring on. So just to finish up the discussion on the marine layer, we're talking about what's the depth of the marine layer. And that will make all the difference in terms of not only how you're going to feel, but also when you go on Mount Tam during the summer, this incredibly unique experience. This is up on Ridgecrest, where you can get up there and you can look down at the marine layer while you're standing on those beautiful grassy rolling hills. This is the dividing line at Mount Tam State Park and the municipal water district land up there. I'm sure many of you have gone up there many times. These are photographs that were shared with me by, I go up there all the time, I love this. These were photographs that were shared with me by one of our newest sports anchors here. He just moved here. And he was just floored at this experience. And he kept coming to me and said, hey, I have some friends coming. I want to bring them up to that view. What's the forecast for the fog? Where will the marine layer be? And in order to do that for him, you've really got to know, all right, what's the depth of the marine layer? And how much of it will there be at sunset? And that's how you can have this wonderful experience of being above it and looking down on it. And that pretty much covers about as much as I had on the marine layer in this talk. So I'm going to pick up now with the rest of the story over the course of the rest of the year. We're going to change gears and I'm going to try and go in order. The first thing is taking us into fall. And speaking of the unique aspects of living along the California coast and living under the influence of the marine layer, as we all do, we also experience something quite unique about our fall here. The map that we're looking at is color-coded, it's produced by NOAA. And what you're looking at is a time series. In other words, if you can hopefully see on the bottom here, the color codes correspond to what point in the year can any given part of the country expect to experience its warmest day of the year. So here's June, July, and August. These yellow shades into orange are what most of the nation can account on. For the desert Southwest and the Sonoran Desert, it's actually early June. For New York, it's, right around July 15th. That's the middle of summer. That's what you'd expect. If you look at the coast of California, we're in a very different color shade on here because you've got to push these colors all the way into October. For coastal California and for coastal Marin County and for coastal Bay Area, you can expect to reach your warmest temperatures throughout the entire year in the month of October. Think back to what we did, actually. We did that this early October. We're smashing records this early October. We had a pretty intense heat wave right on cue, according to what this map is trying to communicate to us. And this actually is tied into the marine layer once again, but more so because of the loss of the influence of the marine layer. Because as we get into this time of year and the marine layer starts to fade, the next important factor in transitioning our weather through the year becomes offshore winds. And I'm just going to take a moment to show you the visual on that, on what this looks like. If you guys can see this clearly enough, this was a time lapse that I did using our weather computers here at KPIX. I show this one on the air all the time. And the streamlines on here animate, just like they did on the other image. The color codes on here show you the intensity of winds. Here's your numbers up here. So the darker the color, the stronger the wind speed. But what I want you to look at first are the direction of the winds, particularly here, before we get to the offshore winds. And if you keep an eye at those streamlines, what we think of as onshore, which is what happens for us most of the year, see what's going on here? I hope the resolution is good enough there. But before this starts animating to show us the northerly winds, you can see we've got onshore winds right there. They're coming in through the Golden Gate, and they're still exerting an influence, even as far inland as Sacramento. There's your delta breeze, and there's the rest of the wind going onshore. In fall, that starts to reverse. And it starts to reverse. It's not like it reverses consistently. It reverses in pulses through these offshore wind events, which are brought about by the very first storms coming into the Pacific Northwest. They miss us. They go over the top of California, and then they dive down into the desert Southwest. We get no rain. But what we do get is we feel the wind. Watch what happens as I advance this, and you're going to see this bright area of wind spill out of the north. So the intensity of the wind picked up here. Look at the streamlines. They're all coming in from the north. And now look at the bay. And I'll bring this back a second. Look at the direction. Hopefully those streamlines are showing up. We'll watch it again. The transition here. And that is an offshore wind event because of one of those inside sliders. These weak storms of fall, which aren't coming far enough south to come onshore in California. They're coming onshore in the Pacific Northwest and then diving down into central Nevada. And when that happens, we feel that gust of wind as they pass. This is our biggest vulnerability through the months of October and November if the landscape is particularly dry, and I'll show you why that is when we look at this one more time. So we're going to play this, and it's going to animate downward kind of fast. This brings us back to the local view, and now you can see what's happening. Those streamlines showing us the direction of the wind are going offshore. And that term, offshore or onshore, when we use those terms, we're telling you the direction that the wind is going to. So these winds are going offshore. They're coming from inland, and they're going offshore. It's the exact opposite of what happens when we get the fog. That's an onshore wind. And that brings the stratus cloud, the fog, the marine layer. That squeezes that all in through the Golden Gate, like we've looked at in so many examples so far in this talk. This is the reverse in fall. And this does two things. Primarily, it dries out the atmosphere because these offshore winds, A, they're coming from inland locations. It's just drier over there. But B, if you look at the way those streamlines are moving over the topography of Marin County, they've got to get over mountain ranges, which means they have to go downslope. And going downslope means that they're sinking, compressing, and warming. So not only are they dry on their own merit, but they're also warming the air, which also dries the air out even further. Drier, warmer air will pull more moisture out of the landscape. It can just hold more water vapor in it. So the very nature of warmer air's ability to hold more water vapor means it's going to look for that moisture anywhere it can find it, and it starts pulling it out of dry grasses, brushes, and trees in the worst case scenario. And this is a very simplified explanation of what fire weather is like here, or what the primary driver of that here. And I've got one example, got two examples, in fact, on here that I want to show you. So I'm going to switch from this presentation for a moment. And if I can, I'm going to pull up, this is off my Twitter account. Two things I want to show you. First of all, it's a time lapse of the marine layer getting what I like to call squashed. It got totally compressed by an area of high pressure. This is early in the morning over the course of summer, when an area of high pressure was building in. So when we talk about, sometimes you'll hear it, a compressed marine layer. Well, this is the very definition of that. High pressure building in through the morning, warmer air, evaporating the top of the cloud, and higher pressure pushing down on it as well. And there goes your marine layer, totally squelched. And the time up there, the ending frame was 8:30. This is 6. That was a 2.5-hour period. There's your fog on the deck of the Golden Gate Bridge. And then the whole thing just kind of disappears. That was just one example that I wanted to share in terms of how the marine layer gets dominated by high pressure. But in terms of the discussion for offshore winds, this is the more relevant one to where we are in the talk right now. So I'm going to pause it for a moment. Picture those streamlines, those wind streams going from inland and blowing out the coast, and then interacting with topography. So let's look down here along the peninsula, down towards the Santa Cruz Mountains. The wind's coming from inland and going offshore. So it's going that way. As it hits the Santa Cruz Mountains, it is downsloping into what was a marine layer out there. And watch what happens to that marine layer as the dry air impacts it. I think this is such a cool visualization. That is actual satellite imagery during an offshore wind event that I saved just because I think it really crystallizes the notion of what we mean when we say offshore winds and what offshore winds do to the surrounding air in terms of warming things up and drying them out. You could look at it a number of different ways. You're just seeing the marine layer. That's easy. There are a number of different ways to look at how the water vapor in the plant life here, grasses, shrubs, trees, there's a number of ways to measure that aspect. One of them is called the energy release component, which is an awful way of describing how much energy is there and readily available to burn should a fire get started, the energy release component. That's the main one that we look at. These are situations where you'll hear the National Weather Service issue things like red flag warnings. A red flag warning is primarily issued for agencies that are charged with protecting the public to let them know to ready all of their resources, because should a fire get started on one of these offshore wind events, the landscape is likely already dry going into it, and this is only going to dry it out even more, and the wind will be able to take any ember and rapidly spread a fire onto a landscape that is now also much drier than it would have otherwise been. So it's that combination. It's really the combination of the two factors, those strong offshore winds, which will gust from 30 to 40 miles an hour. Southern California has called theirs the Santa Anas for decades. In recent years, people up here have tried to come up with a nomenclature for us. You might have heard the term Diablo winds. I don't know how much that's really taking off, which is why I do my best to just simplify it and use that term offshore winds, because as long as we can get that concept across, I think, and hopefully with visualizations like this, that will help. I mean, this is the exact opposite of what we see all summer. The marine layer is not coming on shore anymore. It's getting pushed offshore and it's getting evaporated as it does. All right, so we'll come back to our discussion because I want to try and get to the rest of the winter if I can. I know I said I was going to get to La Nina, and right now I'm still in fire season, but I'm done with fire season, and we're going to move on now to the next topic. So what happens when we get through fire season? Hopefully, we're doing that now. We've gotten a nice little series of rainmakers. We really have lessened our vulnerability over the course of the last 2 weeks. There's more rain coming, by the way, on Wednesday night, which will help. So let's look ahead. And with what little time I've got left, I want to talk about winter and some of the unique aspects of winter here. And the term which has really taken off in recent years is atmospheric river. And hopefully you guys have now seen plenty of representations of this. Let me bring this back. But here's an example of what we're talking about. What you're seeing on here is a depiction of water vapor content in the atmosphere. The deeper shades of red along the equator have much higher amounts of water vapor within them in the tropics, as you'd expect. And then every so often, all across the globe, they don't just happen here, this happens everywhere, you see a little filament, a little ribbon, a little plume, a condensed ribbon of higher concentrations of water vapor, which are getting picked up out of the tropics and directed, in this case, at the West Coast. This is one that I captured about 3 weeks ago, so you can see what's going on here. They're not coming far enough south for us yet, but they are occurring already. They do every year. And right now, we've already seen a couple of these going to British Columbia or Seattle. Atmospheric rivers are the most important feature when it comes to what our rainfall totals are going to look like in any given winter here in California. Here's an example of one of the more notable atmospheric rivers of the last few years. I remember this one well. This was from October 24th of 2021. So I'm showing it to you what it looks like on a simple water vapor plume. I saved this image. This was the futurecast depiction of what this storm was going to look like when it came on shore. We were showing this to people for, these go about 3 days in advance. So up to 3 days before October 24th, we had all this wonderful high resolution forecast imagery of what the radar depiction was going to look like when this storm arrived. And it's pretty darn impressive to see this. That is a concentrated plume of heavy rain taking its sweet time like a fire hose raking down the coast of Northern California and across the bay. This particular atmospheric river on this day dropped 4 inches of rain in San Francisco in 1 day. The average rainfall for San Francisco throughout an entire year is 24 inches. And if you look back at October, if you look for any other records, what's the record amount of rainfall in October? The nearest records to that are about 2.5 inches. So this shattered by a wide margin the record for single day rainfall in San Francisco as a courtesy of this atmospheric river. It was the strongest atmospheric river on record in the month of October. There have been stronger atmospheric rivers than this one, several. But for the month of October, this was the strongest one on record. Now that was winter 2021 going into 2022. The rest of that winter was a dud. Thank goodness we had this atmospheric river, actually. It wasn't pleasant when we went through it. There were flooding issues. There were downed trees. It was a problematic system while it occurred. But it set us up because we were already going into year 2 of what was feared to be 3 years of a drought at this point. I'll go into some of that in a second. So that atmospheric river kept us from going into a deeper drought than we would have. We really didn't get much else for the rest of that winter. I'll show you what that winter looked like here in a second. But here's a look at last winter. And what you're going to see here is a retrospective of every atmospheric river that made landfall in California for winter 2022 into 2023. So this is the winter that we just came out of, ending, this will go through March. No, I'm sorry, this is the winter from before this winter, 2022 to 2023. We're just coming out of the winter that's 2023, 2024. However, this was a very intense winter for us. I don't know, memories are short term on this stuff for all of us, I know. But this particular winter was quite intense, 2022 to 2023. And the atmospheric rivers, you may have heard, are now rated on a scale. This is a recent awareness and a recent way for us to kind of put a concept on these things, rate them, put some perspective on them, keep track and tabs of them. And they're color-coded on this particular image. And you can see on here in this winter, look at the orange ones, 1, 2. We had about 2 moderate strength. We had 1 very strong. We had several others that were weak. That's just an example of what these things can look like over the course of a winter. But I'm going to show you an example of some winters that were very different. Did not get atmospheric rivers like that. So let's advance this. And what I'm going to do is skip to here. So that's a review of the same one we were just looking at. Now I'm going to show you the year that was 2 years before that. And that's where they all went. This was the year that put us into a significant drought. This was the winter of 2020, 2021. And the atmospheric rivers didn't show that year. We got very few storms in general that year. But what we've learned about atmospheric rivers in general is they really determine the entire nature of what that water year is going to be. In other words, 3 or 4 of these will make an entire winter's worth of rainforest. They will be the defining feature of, did we have an average year, an above average year, or a below average year? Water year 2021, that's the winter of 2020 into 2021. We started to go into a very significant drought. This was the first year of it because the atmospheric rivers did not show. So there's your comparison. Here's what it did the next year. This is when we came out of the drought. But that's when we went into it. There were 2 years like that. And that's part of this defining feature of California in terms of those wild swings. California, because of everything we've looked at so far in this discussion, among a few other things which I haven't had time to get to, goes through bigger swings around the average than anywhere else in the country. So that's what this map's trying to communicate to us. It's color-coded map down here. So the deeper shades of blue, which you see for Southern California, but look at the shades of green for Northern California and the Bay. The readings down here are telling you how far you can expect your particular winter to swing around what you would term average. So again, let's say San Francisco's average rainfall is 24 inches. How far off that mark, using San Francisco as our example, does California typically swing from one winter to the next? The deeper you get shaded into those greens and blues, the more wildly you swing around that number. In other words, you typically come out way below it or way above it. Now, if you're in the shades down here in Southern California, you can expect to be 70% off the mark of average. You can expect to swing wildly that much. Southern California really does this. Here at home in Northern California, we're not that extreme, but we're pretty extreme, not only in comparison to the rest of the United States, but in general, in comparison to much of the globe. We can expect our winters here to swing about 35 to 40% around the average. So, you know, it's one thing to say what an average rainfall is in San Francisco, and we use average for that 24 inches rather than the word normal, because it's not really, you know, there really is no normal. If you wanted to say, well, what's a normal winter like in the Bay? Then you could say, well, in a normal winter, you could expect to be in a range that's either going to be, you could hit average, or you can swing wildly and be 30% below it or 30% above it. That's like a normal winter for us. Whereas places over here, they don't do that. Look at the number over here. New York, the Northeast, Chicago, the Deep South, they pretty much hit their average on a far more regular basis than we do. And having lived in California your whole life, as I have, that's a much needed perspective, because you think the climate you live in is normal for the rest of the country or the world, and you recognize how unique California is in that sense. So, all right, I'm running out of time, so I just want to I want to touch briefly on La Nina if I can, and what we can expect from that this winter. So real quickly with my 7 minutes that it looks like I have left. This is the Climate Prediction Center's forecast for this winter's precipitation. It says December, January, February up here. This is, and they just put this out just about a month ago. They do not have a high degree of confidence this winter to call it one way or the other in California, above average or below average. That's what this map is trying to communicate. Texas is expected to be below average. The Pacific Northwest is expected to be above average. This is very close to a classic signature that you would get during a winter that's going to be dominated by a La Nina. Quick review on that. We know the sea surface temperatures. That's what it looks like if you just take the temperature of the ocean. Mid-50s off the coast of California, mid-80s down here in the deep reds. But if you want to spot El Nino or La Nina, you cannot look at just regular sea surface temperatures. You've got to look at how far above or below average those temperatures are. And that brings us to this image. That is what the sea surface temperature anomaly map looked like. It's color-coded. The deeper the shade of red, farther above average you are. Clearly, there's a huge issue going on here along the equator. This is from the winter going into November 2015 into 2016. Many of you probably remember the hype around this. because this was being referred to as the Godzilla El Nino. This was a monster. They measure these sea surface temperatures out here, and the range goes anywhere from a half a degree to like 3 degrees above average. And this one was breaking records. It was like 3 degrees above average. This is the technical definition of an El Nino. We're just talking about sea surface temperatures along the equator off the coast of South America. In contrast, that is a La Nina. Cooler than average sea surface temperatures along the equator. And this was the La Nina from November 2020. So that's really the literal definition of what we mean. El Nino is not a storm. El Nino is strictly talking about sea surface temperatures on the equator. Now, why we do that is because we know if you warm this section of the equator enough, as you do during an El Nino, or if you cool it enough during the opposite, a La Nina, this region of the Pacific is very influential on what the storm track ends up doing throughout the winter. So when you have the sea surface temperatures go into this pattern, the storm track typically gets directed in such a way in the mid latitudes that we get more storms in California. And when you warm the sea surface, or when you cool the sea surface temperatures below average, that changes the storm track in such a way that we get fewer storms in California. That's El Nino, La Nina 101. This is the forecast for this winter. See the months down here. November, December, January, February, March, April, May. This line is showing you the forecast is that we're going to stay in a La Nina, but it's a weak one. Here's your temperature scale. We're only going to be about a half a degree below average. That is a weak La Nina. And if you're curious, we have some recent history with what weak La Ninas have looked like here in California. So just a quick review. And guys, let me know if I start pushing the boundary here. Dave, you pop in and let me know if I'm getting, this shouldn't take too much longer, just to kind of give you the review of what weak La Ninas in recent memory have done for us. Remember, we were talking about the drought from 2020 when the atmospheric rivers didn't show. This is what it looked like going into that winter. That was a moderate strength La Nina. You can either be weak, moderate, or strong. 2020, we had a moderate La Nina. We had a very dry year. The next winter, 2021 into 2022, it was another moderate La Nina. And that drought deepened. I believe this was the year where we had that October atmospheric river and then very little else the rest of the year. Then we come to the next winter. This would have been the third La Nina in a row. This is now winter 2022, 2023. At this point in the year, we are 2 years into a very deep drought. We swing so wildly here. It can be easy to forget this, but all of the headlines, we were talking about the seriousness of California's drought. Is this a mega drought? What are we going to do? And now here we go. We're heading into the third year where there's another La Nina out here, and we were bracing for bad news. However, this was the first two were moderates. This third La Nina, in what was being referred to in kind of a catchy way as the triple dip La Nina, this one was a weak La Nina. So let me show you how that one played out for us. That you remember, La Nina, on average, typically brings us less rain. Well, it did the exact opposite. This is winter 2022 going into 2023. This is the one where we looked at where all those atmospheric rivers came to California. This was the year the Pajaro River was flooding. We were breaking in coverage news on that. This was the year where we were getting so much rain in California. This is a graph that was put together by Jan Knoll. Jan Knoll used to be the lead forecaster for the National Weather Service here in Monterey. He now is a wonderful statistician and shares a lot of great insight on things across the board weather-wise here. And what he did here was a comparison. We were getting so much rain that winter that Jan created this chart to put a little perspective on this for us. By the time we had gotten to, this is like mid to late January, we had already gotten 21 inches. Remember, 24 is average for the whole year, and we still had many more months of winter to go. And this red line shows you we were getting pummeled. Look at all these storms, primarily atmospheric rivers. And it was so rainy, people were saying, hey, is this going to be that arc storm that I've heard about? And if you haven't heard the term arc storm, That's a term that has been devised in the scientific community as an example of the worst case scenario of a series of unceasing atmospheric rivers that are capable of producing potentially the biggest natural disaster risk California faces. Now, we had one of those in 1861, 1862. And if you know your history, you've seen pictures. This was the year Leland Stanford had to get in a rowboat to get over to the state capitol to be sworn in as the governor. Sacramento easily floods. It's a dramatic story, but the line, I think, is even more dramatic. That's where we were. For San Francisco, we got 50 inches of rain that year, 2 winters worth in 1 year. So Jan said, all right, everybody hold your horses. I know we've gotten a lot of rain, but we are nowhere near the arc storm scenario at this point. And at this point in the forecast, we could already see there was a break coming. So we knew we were not going to be getting the unending, ceaseless series of atmospheric rivers. We still got storms after this, but we did not go that far. But just an example of how intense that winter was. My point is, this was a winter under the influence of a weak La Nina. I've got another example. Look what the Sierra was doing that year. We were shattering records for like the snowiest winter in many places in the Sierra. It was nuts. Homes were just were flattened. One other example of another weak La Nina in recent memory. This was November 2016 going into 2017. All right, we've got a weak La Nina. We didn't make much news of it. We thought, okay, that probably tilts the odds a little bit towards a below average rainfall for us. You might remember a pretty significant event that happened this winter. In February of that winter, by that point, we'd had so much rain and so much snow in California. This was the year Oroville Dam almost failed. That intense winter happened during a weak La Nina. A little more perspective on this. The image over here shows you what rainfall in general across California was like that winter. So there's your 176%, 160. These were the basins responsible for what we saw at Oroville. But even here in the Bay, we were at 165% of average. That winter was a weak La Nina. What's interesting about this weak La Nina, it followed immediately that year we were looking at, which was the Godzilla El Nino, where we were so concerned that El Nino was so intense, we were going to have significant storms. That year ended up being average. This was the Godzilla El Nino from so many years ago now, almost 10. And the predictions were dire. Get ready. We're going to have a significant winter, and we didn't. We had a good winter. It was an average winter. So the point on that is El Nino and La Nina, they are helpful predictors, but they are not guarantees. There are too many other wild cards in the atmosphere, especially in a place like California, where we know the notable signature for our winters is to swing wildly around the averages. So here's another image that Jan shared to kind of help us all wrap our heads around what weak La Ninas typically bring for California. He's got all the years up here, which kind of fit that example. You can see many of them are a little below average. Some of them come out way above the mark. And when you average it all out, yeah, there's your 94% for the Bay Area. When you average it out, sure, in the long run, under weak La Ninas, the odds tilt towards a slightly below average. But you really should not use weak El Ninos or La Ninas as forecasting tools. Moderate to strong, particularly strong, can be relied on much more heavily as predictors. They're not guarantees either, but they are much more useful as predictors. So that brings us back to why the Climate Prediction Center didn't want to touch it. When they say equal chances, they're saying you've got a 33% chance in California of being below average, you've got a 33% chance of being above average, and you have a 33% chance of being right on the mark average. They're saying there's not enough information to do it. And that brings us back to this image, which is probably the defining image of what winters are like here in California. It was put together by Michael Dettinger. It's one of the researchers out of Scripps Institute, and he's been really helpful in helping to conceptualize this stuff too. So I'm pretty sure that's my last one. Yeah. So I made it, and I think we did just about exactly an hour. So Dave, I'll hand it back over to you now.
Okay. there are a number of questions in the chat, and I'll try. Some of them have been answered. Nita Winter asks, what and where is the almost constant source of the descending air that creates our high pressure?
Well, I can bring us back to that fact. That is a summer phenomenon, and that can be explained from this one. I'm not sure. Am I sharing my screen with you guys?
Not right now, no.
Let's see, let me figure out. Let me get back to that. Let me come here. Do a share. And how about now?
Yes.
Okay. So to answer the question of what and where is the source of the descending air for our high pressure, because of our latitude, I mean, this could be a long discussion, but there are these things called, well, there's one called the Hadley cell. If you think about the globe, it's much warmer along the equator for obvious reasons. Warmer air wants to rise. As that warm air rises off the equator, it spreads out. Half of it goes into the northern hemisphere, half of it goes into the southern hemisphere, and it continues to travel north as it does so. When it gets to this latitude, it loses that momentum and it starts sinking. That's called the Hadley cell. And it is that overturning of rising air in the equator, that air spreads out and eventually has to come down. It just so happens that at this latitude, right off our coast, is where you've got that sinking air. So that's really the deeper in the weeds discussion of why there's a semi-permanent ridge of high pressure over this section of the Pacific at just the right latitude for California to block the storms. So hopefully that answers that question.
Artie Kirsch has put a quote in from Wikipedia. Let's see where this goes. Santa Ana winds are catabiotic, gravity-driven winds draining air off the high deserts, while Diablo-type wind originates mainly from strongly sinking air from aloft, pushed toward the coast by higher pressure aloft. I think that's just a paraphrase of what you said.
Well, he's also finding a distinction in there in terms of what may be a subtle difference between Santa Ana winds and Diablo winds. But the important takeaway on that is they are both offshore winds, and they both have the same impact on the landscape and, for the purposes of this audience, on the vegetation, on the grasses, the shrubs and the trees. The influence and the effect is the same, and they are both, in a simplified way of discussing them, offshore winds.
Annette is commenting that, kind of riffing on your 2015 example, we got 22 inches of rain in one weekend in 2015, she says.
Where are they?
I don't know.
Okay, yeah.
That's the sum of the comment.
Right.
Roger says, objects in the fog appear to look larger. How is that explained?
Oh, that's a tough one. I've never heard that. And I can't say that I've experienced it personally yet anyway. I'll look for it now. But I can't really think of an explanation for that. Perspective, maybe, who knows, Not sure.
Yeah, there was a freighter in there. I don't know, maybe that's what's being referred to.
Oh, maybe.
Golden Gate. There was
Right.
at one point. Thomas, what, if any, effect does the depletion of groundwater have on the atmospheric climate?
Well, I think the influence is probably going the other way. It depends if we're talking about surface moisture, that's one thing. If the ground is moist or saturated, that can have an influence on temperature. But if it's groundwater and there's no access to interacting directly with the atmosphere, I can't think of an influence that groundwater or lack of groundwater would have on the atmosphere above. None that I've been made aware of or can even rationally think of.
Kimberly asks, can you explain how the temperatures in valleys are so different? Heat lingers in the summer and cold lingers in the winter.
Well, primarily think of the topography. Oftentimes they're bowls. I think the winter example is probably the best one. The valleys are the low spots. At night, cold air, because cold air is heavier, sinks and it pools in those low spots, and it'll pool in the valleys. This is why it is colder in the mornings in places like the North Bay or inland. If you've got enclosed valleys, you'll feel the cold much more in the winter, and you can be a little warmer on the ridge tops then, which seems counterintuitive in winter as well. But there's something called a thermal belt. When you live in the Central Valley, especially if you live in the foothills, Auburn, Placerville, you're in a thermal belt because that cold air settles down and just sinks down and pools up in the Sacramento Valley. This is why they get the fog in Sacramento, and people in Auburn and Placerville like to brag that they are above the fog line, below the snow line. But at least for this answer, it's the above the fog line. You're warmer up there because a lot of that cool air has kind of slunk off and settled down. And it's a bit of an inversion that will develop that way. We see that effect here in some of the valleys in the Bay as well, but it's not as exaggerated as it is in the Central Valley.
And that says where the weekend of 22 inches was in 2015. It was in the Marin and Fildar reservoirs. And my recollection is that like Bolinas Ridge and Mount Tam, it gets about 50 inches of rain compared to the flatlands, about 25 or 30.
Ah, so I wonder if she's saying the reservoir itself rose by that many inches.
Well, they do measure rainfall up there. And I think, as I say, I think Mount Tam gets about twice the average rainfall on the slope than we get down, let's say, in Mill Valley.
Yeah, definitely. And I looked into that. There's a very reliable historic log from Muir Woods. And so if I gave San Francisco's example of 24 inches annually, Muir Woods is up around 36 annually. So yeah, vast differences in topography, and certainly with elevation. The mountains will pull a lot more out of these storms, rainfall-wise.
Oh, this is great. Rogers has done a ChatGPT query, so we'll see where that goes.
Okay.
And it response was objects in fog can appear larger due to a phenomenon known as the diffusion of light. When light passes through fog, it scatters in different directions because the water droplets in the fog act as tiny suspended lenses. Interesting.
There you go. That's kind of like when you go to put the feeder into your fishbowl and you see not only does the rod bend, but the rod probably also appears a little bigger. There might be some connection there between those two. It's the refraction of light through a different density.
Yeah. Well, I think that's all in the chat. If anybody has a question they'd like to ask, feel free to raise your hand and unmute yourself. Nona, please.
If I click view, will I see it?
Nona, you have your hand up.
Okay, there you go. All right.
Oh.
Can you hear me now?
Yes.
Yeah.
Okay, sorry. I put a note in the chat that a map of the isohyots around Mount Tam shows the huge, significant microclimates that are affected by rainfall, like 70 inches over on the Kent Woodland side, 36 inches maybe in Mill Valley side, and then going up and around north of that, like 20, 22 inches in Chileno Valley. So
Oh, wow.
we have huge, interesting microclimates that affect all parts of Mount Tam and the vegetation, of course.
Very cool. Where did you find a map with isoheights on it like that for?
Oh gosh, deep in my files. I've had it for
cool.
years. I've had it for years, and
Well, I'd
really
love to see it. I don't know if
it's an
there's any way.
important map.
If there's any, Dave, is there a way that we could coordinate that? Maybe if she shares it with you, you could share that with me?
I could try to
Sure.
find it and find a source. Yeah, it's a fascinating.
Yeah, I'd love it.
phenomenon.
I'd
Okay.
love it. Thank you.
Another question, comment. Thomas says, thanks you for your presentation. Would you be willing to do another featuring the cause and effect of climate change on what you've specifically covered today?
Sure.
I would certainly endorse that request. That's a
Yeah.
fascinating topic.
Yeah, I would love to. There are a lot of important features to discuss in terms of what we know about how California is going to change as a result. And the most important one actually goes back to that map I showed you that tried to visualize how much we will swing around the averages. And there's a lot of work that's been done on that, particularly by a climate scientist by the name of Daniel Swain. And I hope that's a name some of you, if not many of you, have already come across. If not,
Yeah, we've heard him.
yeah, let me recommend that. He's prolific, he's excellent. And he's got a YouTube page where he regularly does live presentations, at least one a week. So check that out. If you enjoy talking about things like this, he's somebody who you would definitely gain a lot from. Anyway, he's led some of the research in terms of the climate change aspect here in California. The number one takeaway, the simplified takeaway is, and we could do a talk on this as well and go more in depth, is that we're going to see those extremes get more extreme. In other words, it's likely that the average amount of rainfall that we receive in California doesn't change all that much going forward under a warmer climate. But what does change is the way it comes. And by that, it's going to come in bigger winters that are interspersed with deeper droughts. And I think if you think of your own experience over the last 10 years, you can probably relate to that a little bit because we really have been seeing a lot of that. So deep droughts, bigger floods, and there's a whole discussion to be had on that. So we could do that, sure. That'd be great.
Janet, you had your hand up.
Yes. Can you hear me?
Yes.
I just want to say thank you. I mean, it's fascinating to me. I have a couple questions. One is I've always thought that the largeness of the inland valleys, the Central Valley, is 400 or 500 miles long, and it acts as kind of like bellows to help pump in the fog through the gate. Is that true?
That is definitely an aspect of the onshore flow that we'll receive. And the simplified way of thinking about that is like a sea breeze that we all know about. So if we know that it's cool off the coast of California, thanks to the California current, water temperatures in the mid-50s, air temperature above that in the low 60s as a result, at the same time that you've got a heat wave happening in the Central Valley, that hot air is going to rise. And as that hot air rises, just like in the California current explanation, something's got to replace it. And the most obvious place is to pull that air in from the easiest location to reach, which is through the Golden Gate. That's the importance of having that one opening for 1,000 miles where air can stream into the Central Valley through the Golden Gate and then up through the Delta, turning into the Delta breeze. And that is definitely what drives that, is the heat from the Central Valley is the driving force behind much of that for them, yeah.
So the second comment I have is that when I watch the weather forecast in the morning on news channels, I always appreciate it, and I don't see it much, is the temperature of the sea
Surface temperatures, yeah.
I feel like that really impacts our weather, and I wish broadcasters would talk more about that.
Ah, duly noted, duly noted. Yeah.
Thank you so much.
Yeah, thank you for your questions and your comment.
There's another one in the chat. Larry is also about broadcasting. Speaking about microclimates, in the past few years, TV weather reports show temperatures for only a few locations, and he wants to know, in the past, how many locations were covered and why? Kind of why has that changed and why?
I think, yes, that has changed, but it's not like a formalized progression. If anybody's watched us, on CBS News Bay Area, we've started a whole new format here, which is virtual, where we're trying to make the weather forecast more visually immersive, with the goal of being able to really illustrate a lot of the things we're talking about here in more accessible, appealing, interactive ways. So I think the best way I can answer the specific question about fewer numbers is, I'm not aware of that being a general trend across the board. I know it's a decision that I personally have made on the map recently as the result of experimentation with this new format, because oftentimes the numbers become too crowded, and I have felt like I wasn't serving the overall audience in that way, because numbers were getting covered up and obscured in this new format. So recognizing that there are about 8 or 9 real good representative spots that will get the story across and show us how the weather's changing. Like an example, I know there's a difference between Los Gatos and San Jose, but it's a fairly mild one generally for the South Bay. So in my instance in particular, and I apologize, I'm not saying that's the way it's going to stay. I'm saying in the experimentation process of trying to figure out how to do virtual weather, that is one decision that I've made lately, is to kind of limit some of those numbers, never at the expense of an important feature of the forecast. If there was an important feature in the forecast that needed to be discussed and it could be done by that number, it will be there. But if it fits into the general overall story that I'm trying to get across in the 2.5 minutes that I have, to be as clear as I can for as much of the population as I can, at this point, I've made a decision to limit some numbers, and that may change down the road. So let me know. Keep an eye on it. And if you've got any suggestions or ideas, I'm pretty easy to find. You can always send me an email.
Another comment from Jill says, College at Marin has done great classes on meteorology and climate change. They're offering a class next semester on the geography of California.
Cool.
So there's
cool.
local resources on that.
Yeah, that's great.
Are there any other questions that have not been asked? Oh, wait a minute. It says there's one more in the chat. Let's see what that now. Oh, Nita's wondering what is your email address?
Yeah, it's just my first initial and last name. So dpeck@cbs.com.
No dot in between?
No dot, just dpeck@cbs.com.
Okay, great. Okay, well, we've fit within the time constraints, and I really want to thank you, Darren. It's extremely clear and easy to follow presentation.
Thank you so much.
Just remarkably good. So
Thank you.
Thank you so much.
Thanks. That's the goal. That's 25 years of honing this on TV. That's the whole goal.
Well, it
Thank you
shows.
for saying that.
It certainly shows. Before we leave tonight, I want to give you a preview of next month's presentation. It's going to be Tanya Baxter, a botanist, biologist who many of you know, and her title is The Flora of Northern Sierra Nevada. Subtitled Botanical Encounters Off the Beaten Path. And she's spent the last couple of years doing surveys, largely for fire work, of places that have not seen much human contact. And she's found stands of rare plants that apparently have never been found before, creating really the basis for a flora that apparently does not now exist there. And she says that it's going to cover plant communities, botanical highlights, scenic sections of the Feather River, and the unexpected field encounters from her last several years' experience. So it should be a fascinating discussion, and we hope to see you then. Again, Darren, many thanks, and for the rest of you, we hope to see you next month. So
thanks, everybody.
good night.
Thank you.